Section: Introduction. In this section, we discuss the significant advancements of large language models, LLMs, in recent years, which have led to their widespread use in critical areas like medicine and finance. However, we find the noticeable drops in performance due to adversarial attacks concerning. For instance, one simple attack involves rearranging the options in multiple-choice questions, which can reduce an LLM's performance from good to worse than random guessing. This issue of sensitivity to input order is particularly troubling as we increasingly rely on LLMs to assess the outputs of other LLMs. The use of LLMs as evaluators is common, and they are also employed to annotate outputs and guide reasoning in complex problem solving. This sensitivity undermines the reliability of these processes. To address this, we introduce Set-LLM, a new architecture that is invariant to permutations, effectively solving the order sensitivity problem. Set-LLM ensures consistent responses by incorporating permutation invariance directly into its design, all while maintaining model performance and complexity. Our approach is based on the observation that the attention mechanism in LLMs is inherently permutation invariant. Most models, however, use positional encoding to account for input order. We demonstrate that even without positional encodings, the causal attention mask in decoder-only LLMs can fully reconstruct the input order. Thus, we begin our approach by removing positional encoding and causal masks. Our complete method consists of 4 steps. 1. Eliminating sequential position encoding. 2. Removing the causal mask. 3. Introducing permutation-invariant set position encoding, set-PE, and 4. Adding a permutation-invariant set attention mask, set-mask. The first 2 steps create a bag-of-words model, which lacks token order information, while the last 2 steps reintegrate the desired order information. We prove that Set-LLM is permutation-invariant, ensuring the same output regardless of input order. Additionally, we show that our adaptations can be combined with various decoder-only LLMs, making them independent of specific architectures or versions. We conduct experiments with 5 different base models across 4 multiple-choice datasets to demonstrate the versatility of our approach. Our main contributions are as follows. We propose Set-LLM as the first permutation-invariant decoder-only LLM, prove its robustness to permutations, and show that it can be effectively trained with different base LLMs. Set-LLM consistently matches or exceeds the performance of base models with random order inputs and significantly outperforms them with adversarial order inputs, all without added runtime costs. This advancement allows for a more robust and efficient evaluation framework for multiple-choice question answering and the use of LLMs as automated evaluators. Next, we provide background on transformers and positional encoding, focusing on the changes in attention masks and positional encoding in transformer-based LLMs before introducing Set-LLM. Most state-of-the-art LLMs utilize the transformer architecture, which consists of multiple stacked attention layers. We explain how attention scores are calculated using token representations and how masking is applied to ensure that tokens only attend to preceding ones. We also describe how these attention mechanisms can be represented in both matrix and graph forms, illustrating the relationships between tokens. Section Summary. In this section, we introduce Set-LLM, a permutation-invariant architecture for large language models that addresses the issue of order sensitivity in input data, which can significantly degrade performance in critical applications. We outline our approach, which involves removing traditional positional encodings and causal masks, and demonstrate that Set-LLM maintains robust performance across various models and datasets without added complexity or runtime overhead. Section: Positional Encoding. In this section, we discuss positional encoding, which, along with the causal mask, helps transformers understand the order of tokens. There are 2 main types: absolute and relative positional encodings. Absolute positional encodings assign consecutive integers to tokens, starting from 0. These integers are combined with the input token embeddings, allowing the neural network to grasp the sequence of words. The attention scores rely on the token embeddings and their absolute positions. On the other hand, relative positional encodings focus on the distance between tokens when calculating attention. Next, we introduce our method, Set-LLM. Large language models, LLMs, are used for various tasks, often involving sets in the input, such as answering multiple-choice questions. For instance, we might have a question about the capital of France with options like Budapest, Paris, Heidelberg, and Zurich. We can represent a mixed set text instruction as a sequence of token sets. If we have just one set, we revert to a standard instruction with a single token sequence. To simplify notation, we use global indexing, numbering tokens in a set of choices consecutively. We denote the token sequence containing a specific token and the set that includes that sequence. Typically, LLMs require an order for these sets, but we aim for an LLM whose output is independent of this order. Our Set-LLM approach achieves this in 4 steps. 1. We eliminate sequential position encoding by setting all positions to 0. 2. We remove the causal mask and replace it with a prefix mask. 3. We introduce permutation-invariant set position encoding, Set-PE, and 4. We add permutation-invariant set attention masking, Set-Mask. The first 2 steps ensure that the model treats the input as a bag of words, ignoring the order of tokens, which has its drawbacks since word order is important in language. Thus, steps 3 and 4 are essential for reintroducing order information. For Set-PE, we generate positions that allow us to calculate absolute or relative positional encodings. We number tokens consecutively but restart numbering for elements within a set. This way, we avoid imposing an order on the options while maintaining clarity in the token order within those options. After a set of options, numbering resumes with absolute positions. We denote Set-PE positions using a specific function, allowing us to calculate the necessary positional embeddings. When using absolute positional encoding, we replace absolute positions with Set-PE positions. For relative positional encoding, we use the differences between Set-PE positions instead of absolute ones. All LLMs discussed in this paper utilize a method called rope, where Set-PE positions influence the angles of rotation for the token embeddings. Section Summary. In this section, we discuss how transformers utilize positional encoding, specifically absolute and relative variance, to incorporate positional information into token embeddings, which helps the model understand word order. We introduce our Set-LLM approach to maintain permutation invariance in input sets while reintroducing order information through a novel set position encoding, Set-PE, method, ensuring clarity in token sequences without enforcing a specific order on set elements. Section: Set Attention Mask, Set-Mask. In this section, we discuss the concept of set attention mask, or set mask. We recognize that when using prefix masking, Set-PE alone is not enough to differentiate between mixed inputs. For instance, in an example with 2 inputs, one person favors Paris while the other prefers London. However, an LLM using prefix masking and Set-PE would produce the same next token distributions. This happens because all tokens in both cases receive identical Set-PE positions, despite the words great and awful being swapped. Since the prefix mask connects all tokens, the outputs from the attention layer end up being the same, just with the 2 embeddings switched. To solve this issue, we introduce Set-Mask, which uses the attention mask to differentiate between the 2 cases. We create Set-Mask by starting with a prefix mask and removing connections between tokens from different elements of the same set, effectively setting those matrix entries to 0. We illustrate this in both matrix and graph forms. Since the generation process is autoregressive, response tokens can only focus on prompt tokens and previous response tokens. We extend Set-Mask to the response in a manner similar to causal and prefix masks. With Set-Mask, the tokens great and awful in our example now have different contexts in the 2 inputs, resulting in distinct embeddings and next token distributions. We assert that an attention layer using set-PE and set-mask is set-permutation-equivariant. Given that all intermediate layers are set-permutation-equivariant and the final layer of an LLM is permutation-invariant, we conclude that the entire network is set-permutation-invariant. To clarify, we note that set-PE positions remain unchanged before and after applying a set permutation to the input. This is because all token sequences stay within the same set after permutation, and sequences within a set are numbered consecutively from the same starting point. If we denote variables after permuting the input with a tilde, we find that tokens not part of a set remain in their original positions. We also show that while this does not hold for general token permutations, it does apply when we restrict permutations to elements within the sets. We break this down into cases based on the relationships between tokens. In summary, we demonstrate that the attention layer is equivariant when using set-PE and set-mask, and we provide proofs for our claims in the appendix. Section Summary. In this section, we introduce set-attention masking, set-mask, to improve the handling of mixed inputs in language models, allowing them to distinguish between different sets of facts by modifying the attention mask. We demonstrate that our approach maintains set permutation equivariance, ensuring that the model's behavior remains consistent even when the order of elements within sets is changed. Section. Again, since $pi$ permutes whole sequences within a set together, tokens in different sequences of the same set remain in different sequences of the same set after permutation. Therefore, $m underscore pi I pi j equals 0 equals m underscore ij dollar. $CAD symbol $a equals pap caret t dollar again. This claim is equivalent to showing that $a underscore pi I pi j equals a underscore ij dollar for all $I j dollar. In this section, we discuss case 3. We note that since the permutation function rearranges entire sequences within a set, tokens from different sequences remain in their respective sequences after being permuted. This leads us to conclude that the modified matrix entries for permuted indices are 0, which is equivalent to showing that the modified matrix entries match the original for all indices. To assess the effectiveness of our approach, we test it with 5 models across 4 multiple-choice datasets. We believe that multiple-choice questions serve as an excellent testing ground for our Set-LLM method, as there are established benchmarks available, and they reflect scenarios where an LLM evaluator must choose the best response from several plausible options generated by the LLM. We evaluate our models on 4 well-known multiple-choice reasoning benchmarks: PIQA, ARC Challenge, Common Sense QA, and SIQA. Each benchmark consists of questions with multiple answer choices, where only one is correct, and the number of choices varies by dataset. In the original setup, only the question is provided, and the answer choices are tested as continuations, with the choice having the highest likelihood being selected. We modify the prompts to include the answer choices as part of the question, allowing for their order to be changed. For SIQA, we remove the numbering from the choices to maintain permutation invariance. All original and modified prompts are available in the appendix. Since our Set-LLM adaptations significantly alter the model's input and attention mechanism, we require additional training for the models to adapt to these changes. We experiment with extra pre-training using a high-quality subset of the ultra-feedback instruction following dataset, which consists of about 10,000 examples. We denote this additional pre-training in our results. Our experiments involve 2 evaluation modes. 1. Random order, where we test all permutations of answer choices for each question and calculate the average accuracy, and 2. Adversarial order, where we also test all permutations but focus on those that lead to a wrong answer from the LLM, if such a permutation exists. Accuracy is measured by the proportion of questions for which the LLM remains correct across all permutations. We evaluate our method using several popular pre-trained decoder-only language models, including Gemma 2B and 7B, Llama 3.21b, Llama 3.23b, and Llama 3.18b, to explore different architectures and sizes. For baselines, we consider a pre-trained and a fine-tuned Gemma 2B using the original prompts, as well as the same model using the modified prompts. We also include a fine-tuned Gemma 2B with additional pre-training on ultra feedback using the modified prompts. An alternative approach to achieve permutation invariance is to run all possible permutations through the LLM and select the option with the most votes, known as majority vote. However, this method incurs significant computational costs, as it requires running the model multiple times based on the number of options. In our training setup, we update the model weights using LoRa applied to all linear and self-attention layers. We fine-tune models separately for each benchmark, training on a single NVIDIA H200 GPU, with training times ranging from 1 to 4 hours per model. We use B-float 16 precision for training but switch to full 32-bit precision for evaluations to ensure consistency and maintain permutation invariance. Although our Set-LLM architecture is designed to be permutation invariant, using 32-bit precision helps avoid minor inconsistencies that can arise from permuting input tokens. Section Summary. In this section, we describe our experimental setup to evaluate the effectiveness of our Set-LLM approach using 5 models on 4 multiple-choice datasets, emphasizing the need for permutation invariance in processing answer choices. We also outline our training and evaluation methods, including additional pre-training and the use of various baselines, while ensuring that our models maintain accuracy across different permutations of input. Section: Experiments and Results. In this section, we first conduct baseline experiments to assess the difference in accuracy between random and adversarial orders. We utilize Gemma 2B as our primary language model for these initial tests. The results for all baseline models using Gemma 2B are displayed in a table. When we fine-tune Gemma 2B on the datasets, we achieve competitive results in random evaluations. However, we notice significant accuracy drops in adversarial settings, especially for the ARC challenge, where accuracy falls from 55.20% to 23.72%. In contrast, our majority vote baselines maintain consistent accuracy across both evaluation modes, demonstrating their resistance to order changes. While these models yield the best results in random evaluations, they require running the models multiple times for each input, which is computationally expensive. We choose causal mask plus PE ultra fine-tuned as our baseline for further experiments. Next, we outline the 4 steps needed to transform a base language model into a Set-LLM. To better understand these steps, we conduct experiments with intermediate models, including causal mask with NOPE, prefix mask with NOPE, prefix mask with Set-PE, and set mask with Set-PE. We also include prefix mask with PE, which is an encoder-decoder version of the base model. Notably, prefix mask with NOPE and prefix mask with Set-PE are also resistant to order changes, performing the same in both evaluation modes. The results for these intermediate models are summarized in a table. The set permutation-invariant models show no accuracy drops in adversarial settings, confirming our design choices. Additionally, Set-LLM surpasses the strongest baseline across all benchmarks in both evaluation modes, indicating that our permutation invariance does not compromise accuracy. This is particularly impressive since these results come from a single run, unlike the multiple runs required for other models. While prefix mask with Set-PE is close to set mask with Set-PE, we find that set mask is necessary to exceed the majority vote baseline and achieve the best results. We also refer to a figure that illustrates a problem that may explain this performance gap. Further analysis comparing majority vote outputs to Set-LLM outputs can be found in the appendix. We also evaluate Set-LLM using other base models, including Gemma 7B, Llama 3.21b, Llama 3.23b, and Llama 3.18b. The results show that all base models experience order sensitivity, with accuracy drops ranging from 3.4% to 31.7% between evaluation modes. In contrast, Set-LLM shows no accuracy drops and outperforms the base models in all cases with adversarial ordering and most cases with random ordering. Moreover, it surpasses the majority vote in many instances without the significant runtime overhead. When using Set-LLM as an evaluator, we ensure that our adaptations do not negatively impact performance on out-of-distribution data after fine-tuning on a small dataset. We assess the out-of-distribution performance by fine-tuning each model on individual benchmarks and then evaluating them on the remaining benchmarks. We compare the performance of both the base model and Set-LLM against the pre-trained base model, with results provided in the appendix. Set-LLM emerges as the top performer in most cases across both evaluation modes. To our knowledge, this is the first paper to introduce a permutation-invariant architecture specifically for decoder-only language models. However, we build on existing works that combine text and permutation-invariant inputs. Our motivation stems from the observation that simple permutations can mislead language models. We quantify the impact of adversarial permutations on language models and multiple-choice benchmarks, analyzing the effectiveness of majority vote, which we include as a baseline. Previous works have suggested rotating multiple-choice options to test the robustness of language models, and using a majority vote over these rotations could provide a more efficient alternative, though it may not yield consistent answers across all permutations. Section Summary. In this section, we evaluate the performance of various models, including the Gemma 2B, under different ordering conditions, finding that while fine-tuning improves random order accuracy, it significantly drops under adversarial permutations. Our proposed Set-LLM demonstrates superior performance across multiple benchmarks without the accuracy loss associated with order sensitivity, outperforming baseline models and maintaining efficiency with a single run. Section: LLM Evaluators. In this section, we discuss LLM evaluators, which have recently been introduced and are now part of many LLM processes for tasks like evaluation, retrieval, and reasoning. We note that the order bias in LLM evaluators has been recognized, and various methods, such as combining multiple runs and using specific prompts, have been suggested to address this issue. However, our work is the first to remove order bias directly from the model's architecture without affecting its accuracy or speed. Next, we explore the relationship between graphs and large language models. We can think of a set as either an empty or fully connected graph, and one important characteristic of graphs is their ability to remain unchanged under different arrangements. This makes several studies that merge graphs with LLMs relevant to our work. The most closely related studies have adapted encoder-decoder and encoder-only language models to process mixed graph text data. Both approaches modify the attention mechanism and positional encoding to include information about graph connections in the embeddings. Finally, we touch on invariant neural networks, which have been around for a while but were recently unified under a common geometric framework. For instance, convolutional neural networks are designed to be shift invariant for images, while deep sets introduced the first permutation-invariant architecture for sets, and graph neural networks are permutation invariant for graphs. In our work, we combine the permutation invariance of these architectures with the capabilities of large language models.